Okay, chapter 5, beginning with 1. There are a lot of definitions in here that won't take very long. Gases generally have what? Well, let's see. The gas expands to fill its space. There's lots of space between the molecules, so the density ought to be pretty low. All right. Well, A is a good answer. Closely packed particles? No. No increase in volume? No. No decrease in. Okay. We can throw the rest of them out. A is the best answer. How about what is the definition of pressure? Or what is the best selection out of these definitions? It's force per unit area, right? I mean, at its simplest form, mathematical expression. It's not measured in newtons because newtons is force, right? So this would be newton. This would have to be square meters to be SI units. So defined as the number of moles, I don't think so. Force per unit area. Yeah, there it is. D. We have to get some tougher ones here pretty soon. SI unit of pressure is the Pascal, yeah. Okay. Oops. I'll do it for you. We could, but in interest of time. A glass column is filled with mercury and inverted in a pool of mercury. The mercury column stabilizes at 721 millimeters. Above the pool of mercury, what's the pressure in the atmosphere? Right, there's a lot of blue smoke in that one. All you need to know is how high is the column of mercury. Then you can convert it to atmospheres. 729. So we need a conversion factor, don't we? That'll leave us with atmospheres. That means atmospheres has to go on top and millimeters of mercury has to go on the bottom. So what's the relationship between the two? Correct. So we just divide 760 and 729, and we know the answer has to be less than 1. So we can definitely throw out A. We can throw out D. So it's either B, C, or E. Let's see if we can estimate. Let's see. In the neighborhood of 0.8 or 0.9. I guess we'd have to work it out to get that value. Now, is that the correct number of significant figures while we're at it? This is a multiply divide rule. These are 3. This one doesn't count. Like conversion factors are exact numbers. So we only look at this one. 3 there, 3 there. We're good. All right. Who's next? The local weather forecaster reports that the current barometric pressure is 30.4 inches of mercury. What's the current pressure in atmospheres? It's another dimensional analysis or a conversion factor problem. Inches of mercury. And we want it in atmospheres. Okay? So that means atmospheres here, inches of mercury here. Does anybody remember the conversion factor? It's like that. So that's going to be a little more than 1. A is our best answer. 1.02 atmospheres. Okay. Let's see, how about 8? Air pressure in the inner tube of a tire in a racing bike is 112 psi. That's about right. Let's see, number 8. So we're starting off at 112 psi for a racing bike tire. And they're about as big around as my little finger, the tire. Convert to atmospheres. Okay. All we need is another conversion factor, don't we? And this is atmosphere. Remember the relationship there? There we go. And if we do our math right, it should be 7.62. Okay. Cancel. Left with atmospheres. What does Boyle's law state? Number 9. Well, we can do it mathematically in a formula. Like pressure times volume equals a constant. And then see which one of these fits. Equal amounts of gases occupy the same volume. That sounds more like Avogadro's law. A. B. The volume of a fixed amount of gas is inversely proportional to its pressure at constant temperature. Yeah. When these are going to vary, that means temperature and moles must be constant. Remember those 4 factors: pressure, volume, temperature, and moles. Now, if you're going to let 2 of them vary, the other 2 have to be constant. So that means B is the best answer. Okay. Avogadro, we just did Avogadro. That's A. Equal amounts of gases occupy the same volume at constant temperature and pressure. Okay. Well, we might as well do all the laws, huh? What's Charles' law? 11. Charles' law says volume of a gas is related to temperature in a quotient. In other words, they're directly proportional. As volume goes up, temperature goes up. As temperature goes up, volume goes up, is the way it's properly expressed, and that's C. It's directly proportional. Remember when I said about the relationship of the variables? If you have 2 variables and they're equal to a constant, if they're products, they have to be inversely proportional. If it's a quotient, it's directly proportional. And that just stands to reason mathematically. If this is constant, can't change it. That one goes up, this one's got to go down in order to keep that constant. And same here. If volume goes up, temperature has to go up. Keep that constant. It's just a mathematical fact. All right, I know I'm skipping a few. Now, if there are any in here that you want to stop at, just holler and we'll stop and work them. Otherwise, I'll just go through the ones I highlighted. Gaseous chlorine is held in 2 separate containers at identical temperatures and pressures. Gaseous chlorine is in 2 separate containers. Chlorine gas in both of them. Identical temperature and pressure. Okay, so the temperature here is equal to the temperature there, and the pressure here is equal to the pressure there. I like drawing pictures. Clarifies things. The volume of container 1 is 1.3 liters. This is 1.30 liters. And the volume of the second one and contains 6.7 moles of gas. 6.70 moles. Okay. The volume of the second container is 2.33. I didn't draw them to proportion, obviously. Liters. And we probably want to know How many moles are in this container, right? That's the question. So what relationship do we have going here? Well, ask yourself, is this a before and after situation or a state function? You've got volume, moles, moles. That's a before and after. Even though they're separate gases, you can treat them as before and after, is what I'm saying. So what's the relationship of volume and moles? That's Avogadro's law, isn't it? So the volume of one and the volume of two are related by their moles. And the volume of one is 1.3 liters. And the moles of one is 6.70 moles. And then volume here is 2.33 liters. And this is the number of moles. So you can do it that way, or you can solve for the unknown first and then plug in the numbers. Either way, you should get 12 moles. This should be. Okay. And then the last step that I don't allude to often enough is, does it make sense? This one doubled, about doubled. This one should about double. So 12 moles is reasonable. Right. 18. Let's see. Body temperature is 309 K. Is that right? 309 K. Let me see. 309. How do I get Celsius out of that? 273. That person's a little cool. That's 36 degrees C. Normal body temperature is 37. That's all right. It's within a healthy range. So we're going to take them at their word. 309 K is body temperature. So we got a body here. Okay. We better give them some lungs because they're going to need them. Okay. And the body temperature is 309 K. Right? On a cold day, at 276 K. So the air temperature is 276 K. And we want to know what volume of this air does the person have to take in to fill their lungs if their lungs are 2.2 liters in volume. Okay. So we've got a temperature one, and we've got a volume one, and we've got a temperature two. We want to know the volume too. Okay. That looks like Charles' law, doesn't it? So we should have B1 over T1 equals B2 over T2. And we're looking for B2. So I'm going to go ahead and solve for B2. B1 times T2 over T4. Then we can plug in the values. See, this is the part that keeps you out of trouble. When you do your thinking first and then you put the numbers in the formula. Just memorizing the formula is not going to get you there. You got to be sure that you put the numbers in the right place. Otherwise, you come out with the wrong answer. So V1 is 2.20. And oops, T1, sorry. 2.20. There we go. And T2 is 276 K. We've already got the temperature in K. And 309. Okay. Yeah. Right. So if we solve that correctly, that should be, let's see, it's going to be less than 2.2. Because this ratio is less than 1. Less than 1 times 2.2 would give us a value less than 2.2. And 1.97 seems reasonable. Okay. So the air we draw in at less than 2 liters is going to expand in our lungs when it's heated to fill 2.2 liters. That's what that problem is saying. You're holding 2 balloons. Now, I think the worked problems for 20 go into a lot of mathematical gyrations. We're going to try to approach this one logically rather than do the math. Okay, so we got an orange balloon and a blue balloon. Right. I don't think the color matters. The orange balloon is filled with neon. And the blue balloon is filled with argon. Okay. The orange balloon has twice the volume of the blue balloon. So if the orange balloon is twice the volume of that one, that means whatever this volume is, 2 times that is this one. Right? So this is B. So if this one's twice the volume of that one, we have to multiply this one times 2 to get that one. That's what that means. Which of the following best represents the mass ratio of neon to argon? So we're looking for mass of neon to mass of argon. Okay. So this is not the only relationship between the two. Right? They're going to have, if they had the same number of particles, this one would be heavier than that one. Because argon is about 40, isn't it? No, yeah, it's about 40. 39.9. We're gonna rough it out at about 40. And neon's about 10. Oh, 20, excuse me. 20. Okay. So if they were equal volumes, then they have equal number of particles. But since this one is twice as big as that one, maybe we should augment our drawing to reflect that. Okay. So this one's twice the volume of that one, which means it has twice as many moles, correct? If we say the moles of the orange one would actually be twice as many moles as that one. So far, so good. So if we've got twice as many moles here as that one, but each one of these is only half the molar mass, then what's their mass ratio? If they were equal volumes, then we'd have 2 here and 1 here. But since we've got twice the volume here, but only half the mass for each one, the ratio ought to be 1 to 1. Mass ratio. Did I skip a step? No. Makes sense. Okay. All right. And we're skipping a few here. Must be a lot of repetition. 29. A gas sample is heated from -20 to 57, and the volume is increased from 2 liters to 4.5 liters. The initial pressure is 0.14 atmospheres. What's the final pressure? All right. We don't have a single gas law that will tackle this problem. What we need is the combined law, because we've got before and after on 3 different variables. All right, so what's the combined gas law? Right? So are any of these constant from one to the other? Moles, yeah. You're heating the gas and it's confined. So we can throw the moles out. They don't change. So now we have our expression. Now what we need to do is put our values in the correct place. Let's do it like this. Okay, if we're heating the gas, what did it start at? It started at -20, right? -20 degrees C. We'll fix that in a minute. And it ended at 57. How about its volume? It went from 2 liters to 4.5 liters. And then it went from initial pressure of 0.14 atmosphere to that one that we don't know. So that we have one unknown. Now we're going to have to fix these temperatures, right? We're going to have to add 273 to each one of them. So this is 253 K and 73. This is 330. Okay. There we go. Now we can set up our equation. We can solve for P2. Okay, so P2 is going to equal to P1V1 times T2 over, okay, over V2 T1. See if I got those right. Bring that over here. We're leaving that one where it is. Bringing this one down here. Okay, so they're in the right order. So all we have to do now is fill in the values. We've done all the thinking. All right, P1 is, I'm going to leave out the units just to save space. P2, 330. And then V2 is 4.5 liters. And T1 is 253. Go. So if we do our math correctly, we should get 0.0811 atmospheres. Okay. Let's see, scroll a little bit and we get number 30. Sample of oxygen gas has a volume of 1.72 liters at 27 degrees and 800 torr. How many oxygen molecules? Okay. Before and after state. Yeah, we're only given the conditions right now. So that means we need the ideal gas equation. And let's see, liters, pressure is 1.72 liters. That's good. Why? Because R is equal to 0.08206 liter atmospheres per mole. Okay. Huh? Yep. like I said, I did that on purpose, but 27 degrees C. Okay, so temperature is 27 plus 273 equals 300. Let's see, what else we need? We need volume temperature moles. How many moles does it say? Oh, it says pressure 800 torr. Pressure. Moles is what moles is unknown. Pressure is 800 torr. But we need that in atmospheres, right? So how do we get atmospheres out of torr? 760 torr per atmosphere. So that'll cancel the torr and the atmosphere. The denominator of the denominator is the numerator. So that'll flip the atmospheres into the numerator. Okay. Let's work this one out. Need to find out what that value is. 800 and 760. 1.053 atmospheres. Okay. We're asked for the number of molecules, but we can't get that until we know the number of moles. So you got to solve for moles. Moles equals PV over RT. And so pressure is 1.053. I'm going to put the units in this time. I think I got room. Volume is in liters. That's good. 0.08206 liter atmospheres per mole K. And then temperature is 300. Okay, there we go. So let's see, atmospheres cancels, yeah, liter cancels, K cancels, and moles flips to the top, and that's good. So that gives us the number of moles. Now we could go ahead and introduce the correction factor for the number of molecules now, but that might get confusing. So we'll calculate the number of moles first. 6. So I get 7.357 times 10 to the minus 2. This is moles. Now to get the number of molecules, we just use Avogadro, correct? And let's see. I think I'm limited to 3. So 4.43 times 10 to the 22 molecule. O2. Yep, agrees. That's 30. And scroll. Skip a few. All right. This one should be easy enough. What conditions of pressure, temperature, and moles most approximates the ideal behavior of a gas? Pressure, low pressure. Temperature, high pressure. Moles, low moles. You want those gas molecules to interact as little as possible. So decreasing the pressure, actually the moles and the pressure kind of go hand in hand. Low moles will give you low pressure. But to answer the question, E, low pressure, high temperature, and low moles will give you the ideal behavior for a gas, which is E. Right. 40. 41.1 grams of neon gas exerts a certain pressure in a container of fixed volume. What mass of argon is required to exert half the pressure of the same conditions of volume and temperature? All right, let's see what we got first. 41.1 grams of neon. 1 gram of neon. And it's at a certain pressure. It doesn't say what the pressure is. In a fixed volume. So volume is constant. Okay. Mass of argon required to exert half the pressure at the same conditions, volume, temperature. So the temperature is also constant. So we're looking at pressure and moles. And what's their relationship? As the number of moles goes up, the pressure goes up if these are constant. Now that's nobody's law. That's derived from the combined gas equation. So these are going to be our variables. All right, so how many moles of neon do we have? I mean, if we're going to let moles vary, we need to know how many moles there are, don't we? And neon is 20.18 grams per mole. We'll just go ahead and calculate that. All right, so I got 2.037 moles of neon. And we want to know what mass of argon is required to exert half the pressure. So if we're starting from moles of neon, the only way we can get at the mass of argon is through moles. We got to find out how many moles this experiment is going to give us for argon. Remember that if these are constant, and if pressure is going up, then the number of moles have to go up also. They're proportional. So we say at a certain pressure in a container of fixed volume, what mass of argon is required to exert half the pressure? So if we got a pressure from neon and we want to exert half the pressure that we do from neon, then that's going to be the pressure for argon, right? All right, what we know is that, like I said before, if these are constant, then the pressure in moles are proportional. So we can also say that the number of moles of neon are proportional to the number of moles. So if we know the number of moles of neon, we just take half of that value, and we got the number of moles of argon. It's 217, about 8.5, rounded off to 9. That's how many moles of argon we have. So now we can calculate the mass of argon. Let's see, argon is 39.95. Okay. Now, if I did this correctly, divide 2 into that. There we go. I don't know. I didn't do that right. 2.037 divided by 2. Okay, yeah, round it off. Hopefully that'll work. And then 39.95 times that. And I get 40.3 significant figures, 40.7 grams of argon. Okay. Did I lose anybody? Everybody. No hands go up. Just some sly smiles. Okay. The key to that problem is recognizing that pressure in moles are directly proportional under those conditions. Once you know that, then you can equate pressure to moles. The ratios would be the same. Let's see, got any more? Oh, yeah, there we go. 46 to 15. Okay, this is based upon, we have these conditions. We're skipping some, but there's one of them. I think it was 51. No, 49. So we have some preconditions that are given before we get to 49. One is that we have a 1 liter flask containing helium, chlorine, methane, and ammonia at 0 degrees in 1 atmosphere. So we've got this container with helium, chlorine, methane, and ammonia. We don't know what the mixture is yet. We do know that the temperature is 0 degrees. I'm sorry? Oh, 4. Thank you. Yeah. All right. Let's start over again. There we go. Helium, neon, methane, and ammonia. There we go. Oops. There we go. And they're all at, this is standard temperature for gases, 0 degrees Celsius. And standard pressure, 1 atmosphere. They're all at those conditions. So, for which of the gases are the molecule? We didn't even need to know that. For which gas are the molecules diatomic? Wait a minute. Oh, I left out chlorine. 1, 2, 3. I put chlorine, put neon instead of chlorine. It's going to be kind of hard to answer that question. That's the only diatomic gas in there is chlorine. Okay. So we didn't need to know all that other stuff. Why don't we look at the others while we're here? 49 answers is chlorine. Since we got them up here, let's look at 46. Which gas has the highest density? Well, if they're all the same conditions, same volume, right, we have the same number of moles. So the one with the highest density is the one that has the highest mass because it's in the same volume, right? Density is mass per unit volume. If that's the same for all of them, then the difference in their densities will be attributed to individual masses. So which one is the heaviest one? Well, let's see, obviously not helium. This one's about 70 grams per mole. This one's 12 plus 4 is 16, a little over 16. And ammonia is 14 plus 3 is 17, approximately. So, well, it's about 40. So chlorine, again, is going to be the densest one. Right? What's 47 asking us? Which gas do the molecules have the highest average velocity? Okay, now if they're at the same temperature, then which one's going to be moving the fastest? Because remember, temperature is a measure of the average kinetic energy. Right? But the average kinetic energy is related to mass and velocity. So if these are essentially the same for each one, then how do they vary? Well, they vary by mass and velocity in order to give us that value. So if the mass goes up, the velocity goes down. Right? We just said this was the heaviest one, so it's going to be the slowest one. Okay, so the lightest one with the lowest mass is going to give us the greatest velocity. We could have approached this from Graham's law too, but I figured this would be easier. 47, 48. Which gas sample has the greatest number of molecules? They're all the same, right? According to Avogadro, same temperature, same volume, same pressure, same moles. So 48 is they're all the same. Okay. We squeezed out what, 4? 5 questions. Oh, we got more questions. 50. Let's keep rolling. For which gas are the collisions elastic? Well, I think we're looking at them idealistically. Right? The kinetic molecular theory says they're all elastic collisions. Completely elastic, which means when they smack, they have the same energy coming out as they do going in. Right? Anybody had physics? I've asked you that before, haven't I? Okay. We conserve energy in an elastic collision. Now, in an elastic or a partially elastic or inelastic collision, we always conserve momentum. Right? What's the difference? You ought to know that. Okay. Have we covered that yet in physical science?
I think so.
Oh, okay. It's coming. Any collision, we conserve mass times velocity. But only in elastic collisions do we conserve kinetic energy. Okay, let's see. For which gas do the molecules have the smallest average kinetic energy? Well, they're all the same, right? We just said that. If they're at the same temperature, they all have the same kinetic energy. Okay. Trying to be tricksy.
According to Gollum.
Okay, 52. The mass of 1.12 liters of gas, Y, at STP is found to be 6.23 grams. The density of the gas is what? All right. That information, you don't need all those values. If you're asked to find the density, all you need is the mass and the volume. So the mass of the gas is 6.23 grams. Okay. And the volume is 1.12 liter. Okay. And if you look at your answers, your units needs to be grams per liter. So we've got the right values to start with. We just divide them, and that'll be, I don't know, neighborhood of 5. B, 5.56 grams per liter. Remember, anything we do the numbers, we do to the units. So if they don't cancel, you got to keep them. So grams divided by liters is our unit of measure. All right, 52, 53. Let's leave that there. Get them both at the same time. Oh. The mass, okay, same conditions. The molar mass of gas Y is. Okay. The molar mass, or I abbreviate molecular weight, is mass per moles. Got the mass, we need the moles. So how do we get the moles? Ideal gas equation. That's our only option. So PV equals, be consistent. PV equals nRT, number of moles equals PV over RT. Now we can do it in two steps. We can find the moles and then plug the values in, or we can substitute this expression right here, right there, and solve for molecular weight and then do it all in one calculation. I don't remember how I did it in problems. But if we did it that way, then if we're looking for the molar mass, we've got mass divided by PV over RT, which means RT mass divided by PV. Okay, just take that part, flip it, that puts these on top with the mass and keeps those on the bottom. So 0.08206 for the, what's the temperature? Standard temperature is 0 degrees Celsius, which is Kelvin 273. And we got the mass at 6.23 grams. I'm leaving the unit out, you may have noticed that. Pressure is, standard pressure is 1 atmosphere. And then volume, what's our volume? 1.12 liters, all right? That's the correct unit of measure. Because this has liters in it, that one has to have liters. Then we can do the calculation. I'm just going to do it for fun. I get, let's see, 3 significant figures. 125 grams per mole. C. Took me a while to find it. Okay. You can do it that way, or you can go ahead and calculate the moles and then plug it back in the equation. You get the same answer. Whatever you feel like you can do and not make mistakes, then do it that way. Right, 55. This question is deliberately left blank. That's because I wrote out those handwritten problems and came along later and found that 54 probably didn't belong in this chapter. So I just threw it out and I didn't want to have to renumber everything. Okay, argon has a density 55. Argon has a density of 1.78 grams per liter. Argon. The density of argon, 1.78 grams per liter at standard temperature and pressure. Okay. How many of the following gases have a density at standard temperature and pressure greater than that of argon? All right. So we've got Cl2, helium, ammonia, and NO2. All right, the densities, if they're all at standard temperature and pressure, then the moles are going to be constant for the same pressure. They're going to have the same number of moles. The only difference between the two will be molar masses. That's what we key on, the molar masses of each one. Right, this one's about 70. This one's about 4. This one's about 17. And this one is 14 plus 32. Oh, I can't do that in my head. 46. About 46. That's as close as you need to get to answer the question. So how many would be, is it, doesn't have density at, greater than that of argon? So argon is about 40. So which ones are greater than 40? This one, that one. So you have 2 that should be more dense than argon, chlorine and nitrogen dioxide. Okay, that's why the answer is C. All right. 56 is going to take some mental gyrations. Which of the following best represents the graph of pressure versus molar mass? So we want to have, it doesn't say where the pressure is on the bottom. Usually the X comes first, pressure versus molar mass. So usually we say this, and I say molecular weight, molar mass. We want to know what shape of graph would fit in there. For a 1 gram sample, we have 1 gram sample of gas equal to the mass. At constant volume and temperature. So volume and temperature are constant. Okay. So what's going to vary? Pressure can vary, and moles won't vary, will it? Well, molecular weight. Okay, so the molecular weight, we're talking about different gases. What would be the pressure for gases of different molecular weights? That's the only way that it makes sense. Okay, so molecular weight is what? Is mass per unit mole, grams per mole. This is constant at 1 gram. Right. So as molecular weight goes up, the number of moles would go down, wouldn't it? If this is constant, then we can also write it like this. Equals mass. Why not write G in there? Mass. Okay, so if that's constant, then they're inversely proportional to one another, the moles. But if the volume and the temperature are constant, then pressure varies as the number of moles vary. Right? So we also have a relationship here. The molar mass is related to pressure and some constant. Now, I think in the worked problems, I went into a whole lot more mathematical gyrations. But this, I think, is simpler. If we just know that if moles changes, pressure changes under these conditions. That's why pressure changes, because the number of moles change. So if we have relationship of molecular weight or molar mass to pressure is equal to a constant, what does that look like? Looks like Boyle's law, right? Pressure times volume is a constant, right? As far as the shape of the curve goes. And what's that called in math? Hyperbola. So it should look like that. As pressure goes up, as pressure goes up, molar mass goes down. Whereas molar mass goes up, pressure goes down. Goes up, pressure goes down. That, or like that. We don't have that. None of those. But that's why the answer is E, because none of them fit that scenario. I got a feeling I lost a few on that one. Maybe the drawn out mathematical expression works better for you. If it does, that's fine. All right. Who's next? Good. Okay, got 15 minutes. We're also waiting for Katie, I think. Okay, 58. Given this reaction, let's see, 2 NH3 gas plus chlorine gas, 3 chlorine, excuse me. It's already been balanced for us. Look at it this way. gives us nitrogen gas plus 6 hydrogen chloride gas. There we go. That's our balanced equation. If you react 5 liters of ammonia and 5 liters of chlorine measured at the same conditions. Okay, so we have 5 liters here and 5 liters there. So, calculate the ratio of pressures. Final pressure versus initial pressure. This is what we're looking for. Final pressure versus initial pressure. So what's causing the pressure? These are all gases, right? Yeah, they're all gases. So the cause of the pressure is the number of moles. If we can find the ratio of the moles after the reaction versus the moles before the reaction, then we can calculate that value. Because this is also proportional to final moles versus initial moles. Okay, what are we starting with? Let's see, are we going to need to calculate that? Well, the volume is also, the volume is also related. If we try to pack a certain volume into so many moles into a certain volume, we also get that ratio. So we're starting off with, let's see. I don't have enough information to calculate moles, right? Because I've only got 5 liters, and we're saying at the same conditions of temperature and volume. Okay, so the volume's not going to change. We're looking at pressure. Let's see. We need to find out which one's limiting. Yeah, we need to find out which one's limiting. Because if you have 5 liters of ammonia and 5 liters of chlorine, you have the same number of moles of each one. But the ratio that reacts is different. So which one's going to run out? For every one of these, or for every 2 of these, you need 3 of those. Right? So you need 3 times as much of this as you do to fulfill the need. So 1 unit here would be 2.5 liters, right? And you need, well, actually, that's not right. Which one's going to run out? The ammonia is going to run out. Ammonia is going to be, this is limiting. Because they're 1 to 1 and they need to be 2 to 3. This is excess. So we're going to have some left over. All right. How much are we going to have left over? Well, let's see. Wait a minute. Hold on a second. That may not be right. We need 3 of these for every 2 of those. No, I got it backwards. No. Yeah. If we got 2 of these and 2 is equivalent to 5, then the ratio of 3 would be, let's see. What would be the ratio? What would this one be? 2 to 5 is 3 to what? What's 2 into 5? It's 2.5. 3 times 2.5 would be 7.5, right? All right, so we are going to use all of that up. This is limited. My mistake. Ammonia is excess. Okay, so now we need to go back and say, if we have 5 liters of that, of Cl2, and we want to convert, how much of this are we going to use up? since volume is related to number of moles under these conditions, then we have like that. That's how much ammonia we're going to use up. 10 divided by 3 is 3.33. We're going to use up that much. So now we have, what do we have left over of ammonia? Let's see. 7, 6, 1.67 liters. Okay, now what are we going to have on this side? Well, if this is limiting, then for every 3 of these, we're producing 1 of those. All right, so 1/3 of 5 will be this one. If we've used all of this up, and we got this much left over from here. So we're gonna have 5/3 on this side, and this is gonna be twice that. So this is gonna be 10. So 10 and what's 5/3? 1 2/3? Yeah. 1.67. So it's 11.67 plus 1.67 is 13.34. So the ratio is going to be what? It's going to be 13.34 to 1.67. That's not going to give me the right answer. I went off the rails somewhere. Let me see. In the interest of time, let me see where I messed up. Yeah, I got that part right. Chlorine does run out. Okay, I used some algebra. We let each one, if we've got the same number of volume, then we have X moles here, and we have X moles here. I don't see why it didn't work for me. Two-thirds of X is used. Okay, we did that, right? If this is X, then we have 2/3 X is used up. And we have 1/3 X left over. Right, that remains. Okay. What do we got on this side? Well, if we start with X here, then we've got, let's see. That's good. If we start with 3, we only get 1/3 X over here. All right, if this is 1, then we're going to have 1/3 of it over here. And over here, we're going to have 2X. So what do we have left over? At the end, we have 1/3 X plus 1/3 X plus 2X, which is what, 2 and 2/3 X? 2.67 X. Okay. But we started with 2X. There you go. 2 into 1.67. 2 and 2.67 divided by 2. 1.34 is the ratio of moles and pressure. That would have been simpler. That looks like good extra credit, Chris. All right. I need Katie to come save me. 61. Let's see. Oh, I forgot to mark down Jonathan and Zachariah. All right. 0.72 grams of a liquid is vaporized at 110 degrees and 0.967 atmospheres. The gas occupies a volume of 0.559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Okay. So if we've got CH2 is the empirical formula, we got to find out what that multiplier is. So in order to do that, we have to determine, we can calculate the empirical weight here. Right? It'd be 12.01 plus 2.02 or 14.03 grams per mole of formula. Now we need to find out what is the true. All right. We need it. So if we have 0.72 grams of liquid, let's see. We need to find out how many moles, right? How many moles? We've got temperature, we've got pressure, we've got volume, and we got our gas constant. We can find moles. So if we solve for moles, PV over RT, what's the pressure? 0.967 atmospheres. The volume, is it in liters? Yes. 0.559 liters. And then our gas constant, oops, 0.206 liter atmospheres per mole K. And then temperature, 110 plus 273. There we go. So now we can find out how many moles we got. And if we know mass and moles, we can calculate the true molar mass of this compound. And okay, I get 1.72 times 10 to the minus 2 moles. And the true molar mass of our gas is grams per mole. So we had 0.72. 72 grams. This is the Dumas method. You'll see this one again. Only you get to do it in the lab. So we divide that into 0.72. And I get 41.86 grams. Okay. So now we need to ratio this one to that one. To find out what our multiplier is. About 3. Right? So it's C3H6. Okay. Let's see what you got. Skip quite a few. Must be a lot of repetition in this thing. There we go. 80. If M is the molar mass, R is the gas constant, T is the temperature, P is the pressure, which of the following expressions represents the density of a gas? Okay. If we're looking at molar mass, gas constant, temperature, pressure, didn't say volume. Well, volume's not in the answer, but if we're going to use our various formulas to develop an overall formula, this is a case where we have several things like, well, start with the question. What's the density? Right? Density equals mass or volume. Okay. We've got these values in here. We're probably going to need PV equals nRT. And then if the question is molar mass, then molar mass, and I'll use their abbreviation, is mass per unit per mole. So those are our three equations that we can work with. Notice that we've got mass here and mass there, and we've got moles here and moles here. Typically, the way I've worked this one is to solve for moles and plug the expression in here. Like that. Then I can take this one and put it right in here. Okay. Then we can equate this one to mass. And just it'd be PV molar mass over RT. This comes over the bottom, this comes on the top. That's how I get that expression. Then I can take this one and plug it in right here. So density then is going to be PV molar mass over RT divided by V. So when you have the denominator here, it's the same as putting it right here. Okay, so if we're going to solve for density, yeah, solve for density. The V's go out, cancel the V's. That leaves us with pressure times molar mass over RT equals density. So do we have a PM over RT in there? Yeah, first one. Okay. So that's just algebra. Anybody have trouble in algebra? All good. Must have made it this far. All right, 81. Okay. One way to isolate metals from their ores is to react the metal oxide with carbon as shown in the following reaction. Working from this one, and M in this case is a metal in with 1-to-1 mole ratio of the metal and the oxygen. And reacting with carbon yields pure metal plus carbon dioxide. Yeah, CO2 gas. Okay. What we're looking for is the identity of the metal. Remember what, I'm sure I've said this before. How do you find the identity of an element? You have two choices. Atomic number, if you know the protons. If you don't know the protons, get the molar mass. And the molar mass of the element will get you closer than anything else. Okay, so we're looking for the molar mass of that right there. All right, what do we know? Well, we know 34.08 grams of metal oxide. Right, reacts with probably excess carbon. Okay. And 4.37 liters of carbon dioxide. CO2. Oh, that were formed under what conditions? 100 degrees C, and 1.50 atmospheres. Okay. I think we can find the number. I mean, we've got pressure, temperature, volume. We can find the number of moles. Just need this. Solve for moles. We can find the number of moles. Then we can move in the equation. Okay. Now, the first impulse is once we find moles, we just say, oh yeah, I know how many moles of metal there are. But we don't know what the mass is on this side. So we got to go over here and work it from there. But first we need to find, let's see, pressure is 1.50 atmospheres. Volume is 4.37 liters. We're in the correct units. And then 0.08206 for R. And temperature is 100 plus 273. Okay. So we can find the number of moles from that expression. 1.5, 4.37, 0.08206, and 373. That's 2.142 times 10 to the minus 1, 10 to the minus 1 moles. Okay, so now we have moles. How many moles of this do we have? This is moles of CO2. So we can find moles of MO. 2 of these for every 1 of these. Right? So we just need 2 times that. Let's do it standard notation. 0.4283 moles of MO. Okay. So we can find the molar mass of that compound. Is that going to help us? Because we have grams per mole. Remember how you find the molar mass of a compound formula? You add up the molar mass of each one, don't you? So if we know the molar mass of the compound and we subtract the molar mass of oxygen, we'll get the molar mass of the metal, correct? That's where we're headed. Okay, so 34.08 grams per 0.4283 moles equals 79.57 grams per mole. Then we subtract oxygen, 16. Okay. That's 63.57 grams per mole. And then we go to our periodic table and say, okay, this is the molar mass of the metal right here. And that looks like copper. Okay. Okay, 82. Standard temperature, 0 degrees C. Standard pressure, 1 atmosphere. Share, okay. Next question. A 142 milliliter sample of gas is collected over water at 22 degrees and 753 torr. All right, this is what that would look like. All right, there's our water. And then we have a collection device, such as a graduated cylinder. And then the gas is generated somewhere over here. This. It collects over here and bubbles. And then it comes up somewhere, whatever that is. So up here is gas. Down here is liquid. All right. We're also told that the temperature is 22 degrees. Okay. We're told that the pressure on this surface, which would be matched by the pressure internally. Well, actually, the pressure inside here is only going to be the same as the pressure outside here if this level is right there. Otherwise, we have a difference in water level, and that would give us an added pressure from the height of the water. So we have to assume that this value right here is the, let's see. What's the volume of the dry gas? 142 milliliters. This is 142 milliliters total. Okay, and the pressure is 753 torr. Which is the same as millimeters of mercury. Okay, we want to know what is the partial pressure of the dry gas. Since we bubbled that gas through water, it's going to pick up moisture, right? And we know what the pressure is, the partial pressure of water vapor in that gas space up there. Right? The total pressure is this one. And that's equal to the partial pressure of the gas plus, I should say, since I used G over here, let's say this is the dry gas plus the pressure of water vapor, like that. Okay. We're given that one. So at 22 degrees, the partial pressure of water is 20. This is 20 torr. Okay. So, we can find out the partial pressure here of water of the dry gas is equal to 753 minus 20, which is equal to 733. Okay, I think what we've got here is a before and after problem. If we say PV over NT, and those are initials, initial pressure and volume, final pressure and volume. Okay. So what's the initial pressure is we can actually use torr. The initial pressure is 733 because we want the pressure on the gas, on the dry gas. So this is the one we're going to use for initial pressure. So we have 733 torr for this term. And the volume, yeah, the initial volume is this total volume, 142 milliliters. the moles are the same. They hadn't changed. So that term goes out. And the initial temperature is 295. Okay. Okay. The final pressure is standard temperature and pressure, STP. Pressure is 760 torr, and standard temperature is 273 K, or 0 degrees Celsius. So this is 760 torr. And we want to know the volume of the dry gas. So that's final volume. And then 273. Okay. That should get us where we're going to go. So if to solve this equation for the final volume, we would take 733 times 142 and times 273. Then divide by 295 and divide by 760. And I get 127 milliliters. Now we look to see, is that one of our, no, it's not even there. Right, so the answer is not there. This was a before and after problem. Let's see, what do we got for 88? Oxygen gas generated by this reaction. Potassium chlorate. Solid decomposes into potassium chloride plus oxygen gas. Okay. Oops. Yeah, 3. My mistake. There we go. It's collected over water. So I should have left that diagram up here. I'm only going to draw part of it. And so we got the gas coming in here. And let's say we got right here. And this is our oxygen gas that we collected. Okay. 27 degrees is the temperature. Okay. And 1.55 liters at 1 atmosphere pressure. So this is 1.55 liter. And the pressure, that's equal to volume. And the pressure is equal to 1 atmosphere. Okay. The vapor pressure of water at 27 degrees is 26 torr. So this pressure is 760 torr. And the pressure of the dry gas, the oxygen gas in there, because you have oxygen plus water vapor, right? So we want to find out how many moles of this. That means we have to find out how many moles of that. So we need to subtract the partial pressure of water vapor, 26 torr. $634 torr, or Let's see how many atmosphere that is, because I know we're going to need it. .834 atmospheres of oxygen. Let me be sure I did that right. Oh, my mistake. Try that again. 734. Line 66. Okay, so we got pressure, we've got temperature, we got volume, we can find moles. So if we do PV equals nRT, then the number of moles equals PV over RT, which is equal to pressure, 1 atmosphere, volume, 1.55 liters, R, and temperature, 27 plus 273. There we go. So that calculation should give us the number of moles. .296 and a minus 2 moles. All right, so this is moles of oxygen. The question is, how many moles of potassium chlorate were consumed? So we need to convert this to potassium chlorate. And the ratio is 3 to 2. So 2/3 of that value will give us the number of moles. There's my mistake right there. It's not 1 atmosphere. It's 0.966 atmospheres times volume of 1.55 liters. There we go. Now 1.55 times 0.08206 and 300. This is 608. This is 405. That's the correct answer. All right, 88. Let's see what's next, if anything. All right, 94. 94 is a good one. Okay. We have a valve between the 2-liter bulb and the 3-liter bulb. So we got a 3-liter here and a 2-liter here. The valve. This is 3 liters. This is 2 liters. And there's a gas in the 2 liters at 1.8 atmospheres. And in the 3-liter bulb, we have a pressure of 3 atmospheres. Okay. What's the final pressure? As long as the temperature remains constant, what's the final pressure when we open that valve? Okay. We've got two laws working here. One is the law of partial pressures, which we use last. But in between there, we do a calculation with Boyle's law. And here's the assumption. You assume for the contribution of this side to the whole is a before and after Boyle's law. So this is P1. This is V1. P1 equals 3 atmospheres. And then V2 equals 3 liters plus 2 liters. Because now the gas is in both of them, 3 and 2. So that's 5 liters. And this will give us the final pressure, the pressure that's due to this side over here. Okay? So if we do that, P1, V1 equals P2, V2, and we solve for P2, then P2 equals P1, V1 over V2. So for this side, P2 is going to be equal to 3 times 3 divided by 5. Okay? 6 divided by 5, 6/5 is 1.20 atmospheres. Okay? Now the contribution from this side, V1, P1, V2, P2. That's a question. So the volume on this side is 2 liters. The pressure on this side is 1.8 atmospheres. And the volume is total 5 liters. Okay. Now we can plug them in here as P1, 1.8 atmospheres times V1, 2 liters. And then V2 is the same, 5. So the contribution from this side, assuming that's a vacuum, we did this one assuming that's a vacuum, and we opened the valve and it went whoosh, it filled that space. And then we said, okay, let's assume this is a vacuum, open the valve, and what happens from that side? Okay, so 1.8 times 2 is 3.6, and divided by 5 is 0.72. Is that right? P1, V1, 2 liters. Yeah. Okay. So it's 3.6 divided by 5 is 0.72. So now we use Dalton's law of partial pressures. Dalton says that the total pressure in that container is going to be the sum of the pressure from the 3-liter side plus the pressure from the 2-liter side. So we got 1.20 plus 0.72 atmospheres, which is 1.92 atmospheres. I think I did this calculation incorrect. Let me check it again. I know we put the right numbers in. 3 enter, 3 times 5 divide. I did. This is 1.8. Okay, so 1.8 gives you 2.52 atmospheres. There you go. That's how easy it is to make a mistake. Number 95. The partial pressures of methane, nitrogen, oxygen, and a sample of gas are 135 millimeters of mercury, 508, and 571 respectively. What's the mole fraction of nitrogen? Okay, mole fraction, right, of nitrogen would be the moles of nitrogen divided by the moles of nitrogen plus the moles of methane. See if I get my right. Yeah, methane and oxygen. Methane plus the moles of oxygen. That's all we need. So nitrogen is the middle one, 508. And when we say moles, this is directly proportional to the pressure of nitrogen divided by pressure of nitrogen plus the pressure of methane plus the pressure of oxygen. Because this is due to that. So now all we have to do is substitute the pressures. 508 millimeters of mercury. And 508 here, plus the other two. 135. See, is that right? Yeah, 135. Plus 571. So I get 0.42. Oh, three significant figures. Actually, I get 419. Closest one to that is C. All right. The trick to this one is recognizing that the ratio of moles is the same as the ratios of the partial pressures. Dalton's law of partial pressure states that what? Well, we've already done that. The total pressure is the arithmetic sum of the partial pressures of each of the component gases. So the best one that comes close to that is probably D. Yep. We got any more? Yeah, we got 103. Okay, calculate the root mean square velocity for oxygen molecules in a sample of O2 gas at 11.8 degrees. Okay, so we got oxygen at a temperature of 11.8 degrees C. And the R value is 8.3145 joules per mole K. Okay, so what's the formula? Well, the formula is going to be at the back, and I'll just go there so that you'll know it's there. Let's see, we got another one coming up. We got 2, 3, 4. We got several of them coming up. What we need is the formula for the root mean square velocity. And that's going to be, there's mole fraction. Here it is. Root mean square velocity is square root of 3 RT over molar mass. equals square root 3RT over the molar mass. And this has to be in moles per kilogram. Okay. So what's the molar mass excuse me, not mole, kilogram, kilograms per mole. So oxygen is 32 grams per mole. If we want to convert that to kilograms, right, got to get rid of grams. 1,000 grams in a kilogram. Right? So that means 32 times 10 to the minus 3, or 3.200 times 10 to the minus 2, right? Yeah, add 10 to that. There we go. And this is kilograms per mole. Okay, and the temperature is 273 plus that, which would be 8,482. Okay. So now we can fill in the values. 3 times 8.3145. And temperature is 284.8 K divided by 3.20 times 10 to the minus 2. Okay. This will give us the velocity in standard SI units of meters per second. Take the square root. I get 3 significant figures, 471 meters per second. How close was I? I got to go back now. 103. There we go. 471.2. C would be the best answer. Okay. 109. Which of the following is included as a postulate in the kinetic molecular theory of an ideal gas? We have to take them one at a time, A through E. What does A say? The distance between gas molecules is small compared to the size of the molecule. No, it's large. So that was false. B, all collisions between molecules are elastic. Yes, that is true. C, in an average collision between molecules, both molecules have the same kinetic energy. Not necessarily. Now, the average kinetic energy for the sample is true at a given temperature, the average kinetic energy, but the distribution of numbers of molecules versus kinetic energy is more like this. There's the average. But you have some that have more energy and some have less energy. Right. So C is false. They don't have the same kinetic energy. They have the same average kinetic energy. How about D? All molecules move randomly in zigzag directions. The first part of that is true. We have to assume random movement, but we don't know how they move. Zigzag, no, they don't necessarily go like that. right? They're going to go this way until they strike somebody, and then they're going to go off some other direction. So the second part of that statement is false. And all molecules have the same velocity. No, they don't. It depends on their molar mass. Okay, so B is the only true one out of that bunch. All right, let's see who's next. Graham's law states. Graham's law refers to rates of effusion. That's if they pass through a membrane of some kind. Rates of diffusion as they migrate through another gas, or they migrate through empty space, one or the other. But the same principle applies to either one. All right, so which one talks about effusion or diffusion? There's only one, E. The rates of effusion of gases are inversely proportional to the square roots of their molar masses. So when you ratio the distance or the velocity, it doesn't matter which, to the distance of gas A ratio to the distance of gas B is ratio to the molar mass of B over the molar mass of A. Okay. Or you could substitute the velocity here. The average velocity of A versus B. That works. Both of them work. Okay, 116. Hydrogen and chlorine gases react to form HCl. Okay. Now, you don't need this, but this is what would happen. Like that. You and a friend are on opposite sides of a long hallway, opposite ends of the hallway. You got the hydrogen and your friend has the chlorine. You both want to form hydrogen chloride in the middle of the room or in the middle of the hall. So if you got this long hallway, say, or room, it doesn't matter, and you're over here with your hydrogen gas, yes, and your friend's over here with his chlorine gas, and you release them. So how do you release them so that they form hydrogen chloride right there in the middle? One of them's going to travel faster than the other, correct? Hydrogen is going to go a lot faster. So if you want to be in the middle, you have to release chlorine earlier, give it time to get further down, and then when you release the hydrogen, it'll speed up and meet the chlorine gas right in the middle. Okay. So which of the following is true? You don't release the hydrogen first. Your friend should release the chlorine first. And you don't release them at the same time. You don't have to know how big the room is. You don't have to know the temperature because they're all operating at the same temperature. Right? So B is the correct answer. All right. 117. Let's see. Order the following in increasing rates of effusion. So the faster it moves, the further to the right it's going to be. All right. So who's going to be effusing fastest? The one with the smallest molecular mass, molecular weight. All right, so let's take fluorine, what? Let's see, fluorine, chlorine, nitrogen monoxide, nitrogen dioxide, and methane. And let's estimate their molar masses. This is 19 each, so it'd be 38. Right, 38, they're approximately 38. This would be approximately 70. Let's see, 35, actually it'd be 70, actually 71, closer. I've been saying 70, but it's really closer to 71. NO is 14 plus 16 is 30, right? Yeah, 30. And 14 plus 32 be another 16 on this one. So it'd be 46. And then this one is 12 plus 4 is about 16. Okay. So which one's going to move the fastest? Methane. Rate of diffusion, that's the fastest. The slowest one is going to be chlorine. And the next slowest one is going to be NO2. And then fluorine. And then NO. 1, 2, 3, 4, 5. 4, 5. So it should be chlorine first, which would be either A or B. And then it's probably A. Check the rest of them. Yeah. Okay. A is your correct answer. And it's all based upon their molar masses, right? The smaller the molecule, the faster it moves at any given temperature. All right. Who's next? 118. Complete the following. Because real gas particles have attraction to one another, is it A? Well, let's put them up here. A, B, C, D, and E. A, C, D, E. E is at least 2. 2 of the above. Okay. Real gases act most ideally at standard temperature and pressure. No, they act most ideally at high temperature and low pressure. Now, that may be standard temperature and pressure, but that doesn't guarantee it. So A is false on a technicality. B, we assume gas particles have negligible volume. That is true. B is true. 1 mole of an ideal gas at STP has a volume of 22.4 liters. That's true. C is true. D, real gases act more ideally at higher temperatures and lower pressures. That's true. Now, those are true, but does it satisfy? The conditions, because real gas particles have attraction for one another. So these are true, but they don't relate to the question, right? Only this one relates to the question of attraction. At high temperature and low pressure, you can negate the attractive forces. Right? The other two, B and C, are true, but they don't answer the question. That's why D is the answer. All right, how about 124? Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? Okay. This one is kind of stretching your abilities at this point because van der Waals attractions based purely upon the gas itself, not upon any external conditions, because we're not given those conditions. So if we look at H2, Cl2, NH3, and O2, or not enough information, the van der Waals corrections depend upon polarity. And polarity is due to a couple of things. One, the bond polarity. So if we were to draw ammonia, and these bonds were polar in that direction, and when you add those together, we get a polar molecule which has a very high polarity, attraction for one another. So this would not be a good, this would probably be the one that would require the most correction. Now these, and this one, and hydrogen, these are nonpolar molecules. But the bigger the molecule, the more instantaneous polarities can develop. And we're not going to cover that in detail until next semester. But just suffice it to say, the smallest nonpolar molecule will give you the least correction. And that's this one right here. So at this stage, at this course, the best thing to do is just memorize that fact. The smallest nonpolar molecule, it's balanced. The smallest nonpolar molecule will give you the lowest van der Waals corrections. All right. 132. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. So we got a sample of gas here. There. And it's attached to a manometer. And we can assume it's mercury. And it's sealed off here, over to here. And then we have a port right there. So you got a gas in there, and we measured the gas volume at 2.34 liters. There. And the mercury level in the arm of the manometer attached to the gas sample. Okay, this is a different type of manometer. Okay, hold on a second. This is the kind of manometer they're using. Okay. It's a J tube. The mercury level in the arm of the manometer attached to the gas sample is 24.3 torr, lower than that of the arm open to the atmosphere. So if we have mercury in here and over here, then the difference between these two is 24.3 torr. Yep. The mercury level in the arm of the manometer attached to the gas sample is 24.3 torr, lower than that of the arm open to the atmosphere. This is lower than that side. Okay. So what does that tell you? That tells you that the pressure in here is greater than atmospheric pressure by 24.3 torr. Atmospheric pressure is 1.23 atmospheres. Okay. What's the pressure of the sample of the gas? All right. We can't add apples and oranges. That's apples, that's oranges. We need this one to be apples because our answer is in apples, in torr. So what would be the torr here? Right. 760 torr is 1 atmosphere. Right. So 1.23 times 760 is 935 torr. And we've got, in excess of that, we have this much. Well, let's see. We'll keep some decimals in here, 34.8. Until we add this to it, 24.3. 895, 959 torr. Okay, so the answer is E. Right, who's next? Skip a few, skip a few. Oh, that's it.